welcome. Logic Theory Part 3, Predicates and Quantifiers. Predicate is a function from a set U that takes the values true or false. We say predicates P over U. U is called the universe, and that's the domain of the function, universe of discourse. Examples: is prime n is a function, it's a predicate, it's a logical function from the set of non-negative integers, set of positive integers into TF. The value of the function at 15 is prime 15, that's false. Is prime 19, that is true. Here's another example. Is perfect square n is from the set of non-negative integers to the set TF. Is perfect square 16? That's true. Is perfect square 8? That's false. Is rational x is a function from the set of real numbers to TF. Is rational 2.3? Yes, true. You can write this as a fraction. Is rational square root of 2? That's false, because square root of 2 is a irrational number. Here's another example. QABC is a squared plus b squares equal to c squares. And a, b, c are real numbers. Now you see Q3, 4, 5 is true because 3 squared plus 2 squared equal 5 squared. 9 plus 16 equal 25. While Q2, 3, 4 is false, 2 to the power 2 plus 3 to the power 2 is not equal to 4 to the power 2. Now we are going to define two quantifiers. One is called universal quantifier. It's said for any, for all, and we use this symbol for it. So you say for any x in S, Px. This would be true if for any x in S, Px is satisfied, Px is true. This will be false if you can find an x in S for which Px is not satisfied, Px is false. That's what we have here. It's true if Px is true for every x in S, and false if Px is false for at least one x in S. The existential quantifier, there exists at least one, and we use this symbol for it. So the predicate will be there exists an x in S such that Px. So this one is true if you can find an element x in S for which Px is true, and false if you can't find such an element, which means for any x in S, Px is false. So that's what this is here. Here are a few examples. For any n in the set of integers greater or equal than 2, n squared is greater than n, that is true. For any x in R, x squared greater than x, that's false. This is a counterexample. You take 1/2, when you square 1/2, you get 1/4. It's not greater than 1/2. This will be true if x is greater than 1. For any x in R, x squared different than 2, that's false, because you can give a counterexample, x equals square root of 2. For any n in Z, n squared different than 2, that's true. There is x in R, x squared plus 2 is equal to 0. That's false. You can't find an x such that x squared plus 2 is equal to 0. There is n in Z, n squared minus 16 is equal to 0. That's true. N could be plus or minus 4. There's more than one. Now we introduce the uniqueness quantifier. There exists only one, and we use this symbol. So we added this to the previous symbol. There exists x in S, Px. This one is true if there is only one x in S, Px is true. False if there's more than one, or if there is none. That's what it is. So true if Px is true for only one x in S. False is if Px is false for every x in S, or Px is true for more than one x in S. Here are a few examples. There is only one n in Z, n squared minus 16 equals to 0. False, because there's more than one. There's only one n in Z, n squared less than 0. That's false. There's none. There is only one n in Z, 2 to the power n is equal to 8. That's true. N is equal to 3. Now, if S is finite set, x1, x2, xn, then this, for any x in S, Px, is equivalent to Px1 and Px2 and Pxn. So this is true if Px is true for every value of x. Well, that's an AND situation here we have. So when you negate this, you are negating an AND here, and you use De Morgan law, and you negate every term, and the AND becomes OR. And this is equivalent to there is an x in S such that not Px. If you have now there is x in S, Px means what? Means Px1 or Px2 or Pxn is true. Now, if you negate this, you are going to negate every term, and OR becomes AND. Then this is equivalent to, for any x in S, not Px. Negating quantified propositions. This is called De Morgan laws for quantifiers. When you say the negation of for any x in S, Px is there is x in S, not Px. And you say this is true. You see, this is a true if Px is false for at least one x in S, and false if Px is true for every x in S. If you negate there is x in S, Px, the negation is for any x in S, not Px. So this will be true if Px is false for every x in S, and it will be false if Px is true for at least one x in S. Here are a few examples. For any n in Z greater or equal than 2, n squared greater than n. We said that is a true statement. Now we are going to negate this. We're going to get a false statement, false proposition. How to negate this? See, for any becomes there exist, and greater becomes less or equal. And that's a true statement. What is the negation of this? This one is false. Its negation will be true. There exists becomes for any. X squared plus 2 equals 0. X squared plus 2 not equal to 0. Is not equal to 0. Here are some properties of quantified propositions, very important properties. For any x in S, Px or not Px, that is true. That's true, because Px or not Px is always true. For any x in S, Px, that implies there is x in S, Px. So if Px is true for all values of x, then it's going to be true for at least one value of x, one value x of S. De Morgan, we just spoke about that. To negate for any x, you say there exists and you negate the Px. To negate there exists an x, it becomes for any x, and you negate the Px. These are another interesting properties. For any x in this set, such that Qx, this is equivalent to for any x in S, Px implies Qx. So if for any x, if Px is true, then Qx will be true. So Px implies Qx. Here's another one, very interesting. There's x in this set, y in S, Py is true, such that Qx is true. So this means there's x in S, Px is true, and Qx is true. This one here, for any x in S, Px implies Qx. Okay, if this is true, and for any x in S, Px is true, then for any x in S, Qx is true. This one is actually, so if you have P implies Q, and P is true, and P is true, then Q is true. So that's what we're doing here. So this is a true, Px implies Qx, and Px is true, then for any x in S, Qx is true. Here are some properties of quantified propositions. This is easy. There's x in S, Px or Qx. This is the same as there's x in S, Px, or there's x in S, Qx. That's from the definition. For any x in S, Px and Qx is equivalent to, for any x in S, Px, and for any x in S, Qx. There is x in S such that Px and Qx, meaning Px is true and Qx is true, then there is x in S, Px is true, and there's x in S, Qx is true. Now, the other direction is false. If there is an x in S, Px is true, and there's an x in S, Qx is true, that does not mean there is x in S, Px and Qx are true. Here's an example. S is the set of non-negative integers. Px is Q is prime, Qx x is composite. So there is a prime number and there is a composite number, but does not mean there is a prime and composite at the same time. So that direction doesn't work this way. Now here's another example. For any x in SPX or for any x in SQX, then necessarily for any x in SPX or QX. Now in this direction is again does not work, and this is a counter example right here. This is an important, and you will see that in some of the exercises and questions to work on. Phi is any proposition, and there is x in SPX. This is equivalent to there is x in S, phi, and px. Phi or for any x in SPX is also equivalent to for any x in S, phi, or px. Now you assume that phi does not depend on x, obviously. Here's an example. Proof assuming q does not depend on x. Q or for any x in SPX is equivalent to, if and only if, for any x in S, phi, or px. When you want to prove if and on only if, you have to prove it in both directions, or you can do it directly from, if you have carrying equivalence properties here. So let's assume phi is true. So if phi is true, the left-hand side is obviously true, because true or true is true. And the right-hand side is also true. The right-hand side is also true, because phi is true, then this will be true. For any x in S, this will be true. Now, if phi is false, then the left-hand side is true. If phi is false, then the left-hand side is true if and only if this one is true. So the left-hand side is true if and only if for any x in S, px is true, and then you will have for any x in S, px or qx is true. So that's the right-hand side is equivalent to the right-hand side. Nested quantifiers, remember in defining an onto functions, and I have a video about functions, you can go to it. If f is a function from a to b, we say f is onto if for any y in b there is x in a, y is equal to fx. And you see this is called nested quantifier. So we are having more than one in the same expression. Here's examples. There is a in z, there is b in z, a squared plus b squared is equal to 14. Okay, let's put a, 1, 2, 3, 4, etc. A squared is 1, 4, 9, 16. And then we're going to calculate b squared is 14 minus a squared. B squared, 13, 10, 5. None of this is perfect square. So this is false. This is false. You cannot find a and b such that a squared plus b squared is equal to 14 as integers. More examples. There's a in z, there's b in z, a squared plus b squared is equal to 25. That's true. A is 3 and b is 4. For any x in R, for any y in R, x plus y less or equal than x plus absolute value of x plus y less or equal than absolute value of x plus absolute value of y. That's a true statement. For any x in R, for any y in R, x plus y is equal to 10. Of course, that's false. You can give a counter example. X is 2 and y is 6. Doesn't make that. You can get another counter example. There's x in R. There is y in R. X plus y is equal to 10. That's true. 3 and 7 or 2 and 8, 1 and 9. So you can find example to prove this. Order of nested quantifiers. If all quantifiers are universal, the order is not important. It's commutative. Here, which means for any x in S, for any y in S, pxy is the same as for any y in x, for any x in S, pxy. You need to take that one out here. Oops. And you need to take, oops, that one. Okay, so for any x in S, for any y in S, pxy is the same as for any y in S, for any x in S, pxy. If all quantifiers are existential, then the order is not important. There exists x, there exists y is the same as there exists y, there exists x. Okay, so we keep going here. For mixed quantifiers, that's very important. The order is important. It's not commutative. For any x in S, there is y in S. pxy is not the same as there is y in S for any x in S. Here's an example. For any x in R, there is y in R, x plus y is equal to 10. That's true. You give me any x, I can find y. Y is 10 minus x. Now, if I put y here first, there is y in R. For any x in R, x plus y is equal to 10. It's impossible. Whatever y you give me here, I can take x. That makes this not true. Negating nested quantifiers. Propositions, its negation. Look at this, very simple. For any x, for any y, for any z, there is x, there is y, there is z, not h, x, y, z. Here, for any x, there is y, for any z. For any becomes there exist. There exist becomes for any becomes there exist, and this is negated. Remember, you have to negate this. Here's another example. There is an x, there is an y. For any z, for any x, for any y, there is a z, not h, x, y, z. Let's translate statements into logical expressions. This is really simple. S is all students in your class. JX, X has full-time job. HXX has a hard copy of the textbook. AXX can attend all classes. EXX has an e-book, electronic copy of the textbook. Here's a statement now. John does not have a hard copy of the textbook. We put not H John. All students have hard copy of the textbook for any X in S, HX. Every student must have a hard copy or an e-book for any X in H, FX, HX, or EX. There is a student who has both hard copy and e-book. That's an and. There is X in S, HX, and EX. All students who do not have full-time job can attend all classes. For any X in S, if you do not have a full-time job, then AX. See that we use implication here. Here's another example. S, all students in your college. C, all courses offered. EXY, student X is enrolled in course Y. Here's Mariam T is enrolled in Math 120. That's it. E, this here. Mariam T, comma, Math 120. There is a course offered, but no student enrolled in it. There is Y and C for any X in S, not EXY. There is a student enrolled in Math 140 and Math 160, but not in Computer Science 120. There is X in S, EX Math, and EX Math 160, 120, 160, and not EX Computer Science 120. There is two different students enrolled in exactly the same courses. So there is X1 in S, X2 in S. For any Y, for any computer, for any course, X1 is different than X2, and if EX1Y is equivalent to EX2Y. And that is the end of logic theory part 3. Thank you and see you soon.